Hello, welcome. It is May 22nd, 2025. We are in Active Inference GuestStream 108.1, discussing next generation artificial intelligence for emergent semantic communications with Christo K. Thomas. So Christo, thank you very much for joining. Looking forward to hearing about the work and also to everyone's comments and questions from the live chat. Thank you. To you.
Thanks, Daniel, for the introduction. And thank you for inviting me for this talk. So I'll be talking about next generation artificial intelligence for emergent semantic communication. And also, I would like to express my gratitude to my collaborators, my postdoc advisor, Dr. Walid Saad, and PhD student in our group, Omar Hashash. So I would also like to advertise a bit on the upcoming research group I will be establishing as a tenure track assistant professor at Worcester Polytechnic Institute in Massachusetts. So therein, my focus will be to work at the intersection of next generation artificial intelligence and wireless systems, with specific focus on resilient and interoperable semantic communication and integrated sensing and communication frameworks, explainable and generalizable AI for next generation wireless systems, foundation models for networking applications, and developing strong mathematical foundations of cognitive and reasoning driven AI architectures. So this is an outline of the talk. So first I will go over a motivation of next generation AI native wireless networks. So then further I will talk about two of my recent research work on semantic communication, and further I will provide some future perspectives which involve emergent language design and using active inference. So if you look at the wireless evolution, right now we are at the 5th generation of wireless systems, which promised, apart from cellular enhancing the cellular communication, aspects like massive machine type of communication or ultra reliable low latency communication. However, 5G could not meet all the promises it actually made. As like the saying goes, usually the odd numbered generations are not very successful at their what they promise. So if that is true, so usually the even number of generations, so next one will be the 6G, so we can expect more exciting developments in 6th generation of wireless systems. So in 6G, so we are not as we move towards making our environments more smarter through making the network intelligent and be able to control the actions of distinct autonomous agents in the environment. So in order to support those applications, 6G brings in a lot of more distinct set of challenges like trustworthiness, security and resilience of underlying AI models, immersivity, sensing, AI nativity, and sustainable computing. So here AI is going to play a crucial role in the design, management, or maintenance of different network and device functions. So such a transition from the 5th generation to AI native 6th generation is expected as we move to 6th generation of technologies. So here the question is, why AI native? Because it can brings in the aspects of adaptability to dynamically varying wireless environment or tasks. It can handle nonlinear signals. It can also bring in a lot of resource efficiency compared to classical systems. So these are some of the advantages that AI nativity provides. However, if you look at the state of the art of AI native networks, so currently the literature is predominantly data-driven AI algorithms like meta-learning or autoencoders, CNNs, and right now there is a huge hype on using large language models for wireless network optimization. However, these data-driven machine learning algorithms are plagued by the following disadvantages, like large data size, which is which may not be always available readily in a wireless systems. Second is their limited generalizability to changing wireless environments or tasks. Associated with the limited generalizability is the aspect that we need frequent retraining of these machine learning models, which means if we have to build communication, real-time communication and control, such data-driven machine learning algorithms are not suitable. So another aspect is they act like black box models, so they lack interpretability, and then they require huge computing power. So unsustainable computing is another disadvantage of these machine learning algorithms. So as we transition from the current AI native to next generation AI native, we must advance artificial intelligence together with the wireless network evolution. So that's the focus of a few of our research papers, rigorous vision papers that that got accepted in the last couple of years. So one paper, in one paper, we actually discussed how we can actually use next generation machine learning algorithms like causal reasoning for diverse or cross-layer network optimization task. And another paper that actually got accepted at the IEEE proceedings of IEEE, we actually looked at a rigorous artificial general intelligence based vision, which I will summarize as follows. So next generation wireless systems are not just about communication. So those will also involve a lot of sensing. So sensing act like an eye for the network. So using the sensed information that contains the states of different autonomous agents or cyber physical systems in the environment, the network should then act like a telecom brain. So where telecom brain is characterized by distinct capabilities such as perception, which means the ability to generate abstract representations about different semantic concepts present in the data, then using these abstractions to perform or to compute or learn a world model that actually allows it to understand the cause and effect relations among different physical processes in the world. So this world model will allow it to perform or predictions about future networks or environment states, and then use that predictions to basically perform action planning on the network. So here action planning refers to not just network actions like resource allocation or beamforming, but also designing optimal control actions for the autonomous agents in the environment, so as to guide or control them in the way as that the network intend it to perform. So that's the idea of the telecom brain principle that we actually envision. So along this direction, one aspect is the perception or the extracting semantics from the data. So further in this talk, I'll be talking about how we can extracting semantics and then communicating this semantics, how it can actually enhance the resource efficiency of next generation wireless systems. So that will be the focus of the next few slides. So to introduce semantic communication, so if you look at the classical communication view, so therein the objective was to ensure that the messages are recovered at the receiver side with the arbitrary low probability of error as possible. So that is the technical problem. So while doing so, we have so far ignored the semantic aspect, which means what meaning do these transmitted symbols convey, and the effectiveness problem, which means how effectively does the received meaning affect conduct in the desired way at the receiver side. So as Shannon has also mentioned, the semantic aspects are irrelevant to the engineering problem. However, when we move towards future networks, wherein we need we have a lot of stringent communication requirements as well as a lot of other intelligent requirements like trustworthiness or immersivity, as I discussed before, we cannot continue to rely on just the technical problem. So in order to make the communication resources more efficient, we must transition to a novel paradigm called semantic communication. So in semantic communication, the objective is to transmit the meaning behind the messages. So here meaning actually means only the information that is relevant to the end user. So communicate this information, relevant information, by building a semantic language between the transmitter and receiver. We call the transmitter to be a teacher and apprentice, receiver to be an apprentice. So yeah, so by creating a machined language, yeah, the objective is to ensure that receiver is able to regenerate the meaning with high fidelity as possible. So here the question is, so what is this semantics actually contained in the data? So yeah, so if you look at the state of the art, one traditional framework is this join source channel coding framework. So in traditional system, we used to separate the source encoding and the channel encoding part, but in join source channel coding framework, we actually combine the source and channel encoding to one module. And in deep join source channel coding, we use a machine learning based encoder and decoder, and then train them in an end-to-end fashion with the goal of minimizing certain semantic loss function. So by training such machine learning models, we ensure that transmitter extract only the relevant information or relevant features from the data and communicate that information only. So that leads to better compression in terms of what is being communicated. However, our vision is that semantic communication is not just about compressing, but better compressing the data. So instead, so if we can instill machine reasoning at the transmitter and receiver side, let's say receiver has better prediction capabilities or ability to generate missing information, so which can be achieved through instilling advanced machine learning framework. So then we can achieve more minimalism in communication compared to just doing deep join source channel coding. And then if we can instill these generalizable machine learning algorithms that actually ensure that we don't need to retrain the system as tasks or the wireless environment changes. So that is also very crucial for enabling real-time communication and control. And another goal is to ensure high fidelity at the receiver side. So in my previous work, I have so far tackled these three challenges, which I will talk about in detail. But there are also other open challenges, like how to ensure interoperable multi-user semantic system when each of the users speak different semantic languages, or how to build a resilient semantic communication system. So resilience against any network disruptions that could be due to time varying channel conditions or cyber attacks, and then how to integrate these SC principles into the current 3GPP standards without introducing significant interoperability and standardization challenges. So those are some open problems that I am currently looking at. Yeah. So let me first talk about my first work on semantics that got published in IEEE Transactions on Wireless Communication. So this is about building a reasoning foundation for emergent semantic communication. So in particular, I consider a two-user semantic communication system. So wherein the transmitter observes the world state and extracts the entities present in the data, and then using the entities extracted, it computes a semantic state description, which I will talk about in detail later, which is denoted by Z belonging to syntactic space, and then this syntactic space, Z is encoded to a representation space and then communicated at the receiver. Receiver extracts a semantic state. Using the extracted semantic state, receiver performs certain reasoning, which is denoted by phi of Z hat, and this reasoned output is used to perform certain actions on the world state. So here there are two problems that I consider. So one is the reasoning problem, so which involves how to learn the semantics present in the data or how to define these semantics, and at the receiver, after reconstructing the semantic state, how the receiver can perform deductive reasoning. And given this deductive reasoning, how the transmitter can better encode this encode is another problem, which is the emergent language problem. So wherein at the start of communication, transmitter is not aware of how what are the semantics that receiver is interested in, and the receiver is not aware of how the transmitter is, in which language that the transmitter will be going to encode semantics. So learning this encoder and decoder, those are which are formulated as probability distribution given as shown here, pi of u given z and pi of z given x comma c. C here actually corresponds to the communication context. So that will be the history of semantics that communicated in the previous time instance. So that is the emergent language problem. Yeah. So for the reasoning framework, we use causality from machine learning. So where causality is founded on 3 different principles. So one is the causal discovery. So given the entities present in the data, so here we call these entities as semantic content elements. So only those entities that are really relevant for the end user task. So those are the semantic content elements. So we learn the cause and effect relations between these entities as a directed acyclic graph as is shown here. So from causality literature, this can be called as the structural causal model. And these structural causal models, apart from these semantic content elements, it could also involve certain exogenous random variables that are actually unknown or hidden from the hidden from us. Yeah, so that's a causal discovery phase. So second phase is the causal representation learning. So when we are given a large dimensional observation, maybe it could be large dimensional antenna measurements. So it may not be immediately immediately be known to us what are the cause and effect variables. So we need to first convert it to a lower dimensional latent representation involving just the causal variables. So that is the causal representation learning part. So during this causal representation learning phase, we can actually filter out the relevant and irrelevant variables from the features extracted from the data. And then finally, we have the causal inference phase. So wherein if we are given this causal graph, we can perform intervention. That actually means we can manipulate the values of certain endogenous variables here, then analyze what is the impact that cause on their effect variables. And then we can also perform counterfactuals. That means, so given we have observed certain set of entities as is shown here, so what would the world state would be if these, let's say S4, if you want to imagine a different outcome for S4, so what interventions on these causes would have caused that? So such imaginary worlds we can assume using the framework of counterfactuals. So if we can actually extract this causal graph and then perform training on this interventional and counterfactual distribution, then we can actually attain a level of distribution generalization. So that's the advantage of bringing in causality. And another thing is the explainability aspect. That so given this causal graph, we can actually tell, like, if you have a causal graph among distinct environment variables, then resource allocation, communication and computing resource allocation variables, and quality of service values, then we can actually assess if the performance falls below a certain threshold. So what are the underlying causes that actually led to that particular behavior? So that's where this explainability aspect is coming by using the framework of causality. So now, so using the causal framework, we learn the causal graph from the data. So learning the causal graph, we formulate it as a factorized posterior distribution, where each factor will be the probability of each of these node variables given its parent. So probability of S1 given probability of probability S1 given S0, where S0 is the parent of S1. So that probability distribution we can use, we learn using a recently popular AI method called generative flow networks, wherein we start with an unconnected set of entities and iteratively learn each edge starting from this unconnected set of entities. And then at the receiver side, after receiving this causal state, receiver actually combines these smaller states and then perform a logical reasoning, where this logical reasoning is performed by evaluating certain logical formula, which is composed of these causal states that are connected by certain logical connective. So it's like evaluating. So okay, if this happened, if the set of, okay, if these are the set of, I mean, if this is the causal state that the transmitter has observed, okay, then what would happen in the future? Okay, yeah, so those kind of reasoning or inferences can be performed using this logical inference framework. So for that, we use neurosymbolic AI. We cannot, so we use a existing neurosymbolic AI method called logical neural network that actually converts this logical formula to a neural network. Yeah, so that's how we actually perform the logical reasoning at the receiver side. So now, yeah, I will I will discuss the emergent language problem. So in the emergent language problem, the teacher's objective is to ensure that it communicates very less semantic information as feasible. The transmitter is kind of, yeah, so that's the goal of transmitter. So which is formulated as negative of average semantic information at the transmitter side. So semantic information conveyed by the transmit semantic symbol U about the causal state Z, given the policy, given the encoder policy as well as the history of causal states. At the receiver side, receiver's objective is to maximize the reconstructed semantic information. So after receiving U, how much information that can provide about the causal state is at hat T, which is the reconstructed one, given the policy of transmitter as well as the policy of the receiver and the history of causal states reconstructed. With the then there are certain constraints like, communication cost plus minus log pi LT, which is an apprentice surprise factor. So which actually tells us how much the apprentice is surprised after receiving certain semantic information. So yeah, so here, given this contrasting objectives of teacher and apprentice, we can formulate this as a two-player signaling game, and the Nash equilibrium of this two-player signaling game is can be formulated as is shown here. So yeah, like apprentice responding to the given the teacher's optimal encoder policies, what's the best response that actually apprentice can provide. That's what this expression actually tells us. So we actually solves this through a, since given, so we actually formulated novel semantic information measures for the transmit side and receiver side, but we observed that those are non-convex functions. So we solved them through an alternating optimization procedure where alternating optimization is performed for some surrogate functions that are convex. So yeah, so this actually evolves, this game evolves through a two-way conversation between teacher and the apprentice, wherein apprentice asks certain questions about the data set, and teacher responds by providing an encoded version of the information. So that's how this game actually proceeds. So as I mentioned here, we cannot continue to rely on the traditional mutual information measures since we need to quantify semantic information here. So as I mentioned here, how I formulate semantic information is that, so semantic information is formulated as the information contained in the logical entailments or logical conclusions that follow from any causal state. For example, if you look at any word like red, there are multiple possibilities, conclusions that can follow from it, like red blooded or red ruby, red meat, and so on. So those conclusions, the information concluded in those conclusions that are relevant to the end user, so that will be the semantic information. So we actually analytically formulate this from a category theory perspective, where we what we did is we defined a syntax category consisting of causal states as the object and a semantics category consisting of the conclusion that follow from any causal state. And capricious corresponds to, from a category theory perspective, corresponds to the conclusions or how we conclusions that follow from any causal state in the syntax category. And this logical entailments, we can map it or we can consider it as a functor from the syntax category to the semantic category. So that's how we actually formulated this semantic information measure. And we also discussed received semantic information, which can be written as a fraction equal to semantic similarity of the transmitted information, where semantic similarity can be computed by quantifying the overlap in terms of the coprecious of transmitted semantic causal state and reconstructed causal state. Yeah, so further further we perform certain Nash equilibrium analysis. So wherein we first did some equilibrium analysis for some trivial cases like the cardinality of the representation space is 1. So that actually means we transmit same semantic symbol for all causal state. So that is minimalistic, but receiver need not be able to reconstruct the meaning with high fidelity. And we also considered the separating equilibrium where cardinality of U is same as cardinality of W. So that leads to high fidelity of meaning reconstruction, but it leads to maximal transmission. So another thing is the partial pooling case where the cardinality of U is less than the cardinality of W. So that leads to a minimal representation, at the same time ensure a high fidelity, sufficiently high fidelity at the receiver stage. So in this partial pooling case, so some interesting insights we got. So we actually showed that the partitioning of the syntactic space occur in such a way that we communicate UK for all causal state that lead to the same semantics at the receiver side. So this partitioning of the semantics causal state corresponds to a partitioning in the semantic space, unlike a partitioning in the Euclidean space for traditional communication systems. So that's an interesting insight that we got from this Nash equilibrium analysis. So further, I conclude these results by discussing the summary of key analytical results. As I mentioned, we formulated novel semantic information using category theory, and we also derived our upper and lower bounds of average amount of bits communicated in an emergent semantic communication system, and showed that these upper and lower bounds are less than that of a classical system, showing minimalism. And we also derived semantic error probability measures. So that showed that the lower bound on semantic error probability is always less than or equal to the lower bound on the probability of bit error measure achieved using classical communication system. So what that tells us is that even if the probability of bit error is maybe high, still the receiver may be able to reconstruct the semantics with high fidelity as possible. So that means we can it's okay to we can avoid these retransmissions as in classical system, and we can maybe transmit at a lower rate. So that means that we must transition to semantic performance measure if we are to make efficient use of communication resources. So that's another insight that followed from these results. So further, I would like to discuss some simulation results. So for the simulation, we actually looked at a visual question and answering based dataset where a teacher communicates certain images, encoded versions of the images, and then apprentice's objective is to answer certain questions based on these images. So we evaluated this the performance of the emergent language for different tasks, where we started with a simpler task where the image only contains maybe one object. So images here contains objects of different shape, color, and size. And we increase the complexity of this task. So as time progresses, what we saw is that the amount of communication rounds required for this emergent language training reduces close to 0. So that tells us that the system is, this semantic communication system is gaining more knowledge, or receiver, the apprentice is gaining more knowledge as time progresses. So then, because of this more knowledge, it can actually avoid retraining for the emergent language. So that way we can get rid of a lot of communication overheard. So that's the generalizability aspect. And we also evaluated the average amount of bits communicated over the wireless network, wherein we showed that for our proposed system, we almost gain around 100x gain compared to classic traditional semantic communication system that does not incorporate reasoning into their architecture, and compared to classical system, yeah, even much more gain is obtained. So that actually shows the minimalism aspect that I was discussing. So that actually concludes the work on emergent semantic communication. And next, I will briefly discuss one follow-up work that we did, where we utilized this causal semantic communication framework for a digital twin-driven wireless network. So this got accepted at IEEE Journal on selected areas in information theory. So here, one application is, as is shown here. Let's say we want to control the operations of certain autonomous robots in an industrial environment. Using the communication from a base station or an edge server. So herein, we assume that, okay, given that this particular industrial environment will be also lot of sensors will be deployed in this environment. So using the sensed information, the base station actually construct a digital twin of the industrial environment and uses this digital twin. It actually, using the digital twin, it actually computes optimal control actions for these autonomous robots in the system. So this is within the framework of semantic communication system, and that's what I will be discussing here. So here, this semantic communication framework, again, we consider it for a two-user, so point-to-point system, wherein the transmitter, it's called an expert agent because it has access to a lot of sensing information. And using the sensed information, it creates a world model about the wireless environment or autonomous agent environment. So basically extract the semantic content elements and generate the causal graph. And using the causal graph, it actually computes an expert policy, control policy. And at the instead of computing the control policy, the transmitter actually computes a causal semantic representation of the causal graph. And the receiver also has a world model at its end, but it creates this world model from the limited communicated information. And then it also computes an receiver here is called an imitator because it tries to compute a policy. And the objective is that this policy should be as close to the expert policy at the transmitter as possible. And this is achieved using the framework of imitation learning. And that's why it's called an imitator agent. So that's so this imitator policy should be such that it is quite close to the optimal expert policy. So as to ensure that the semantic effectiveness of the task at the receiver side is as high as possible. So that's a system model. So compared to our previous work, herein we went one step beyond in terms of defining the semantic information. So in traditional mutual information frameworks, it does not distinguish between directionality of information, like but I of x comma y is basically same as I of y comma x. So but in a causal system, we must be able to distinguish between I of x comma y. If x causes y, then I of x comma y should be different when it should be different than I of y comma x. So this is achieved through the principle of intrinsic information. So given, okay, let's say assume that SIT is the state of the system at time t, and IC of SIT minus 1 given SIT tells us about the cause information about the cause state, which is ST minus 1, provided by the current state ST. Similarly, we can define the effect information, which is basically the information about the future effect states. So this can be defined using a distance measure between these two probability distribution, which is probability of SIT minus 1 given SIT and probability of SIT minus 1. Similarly for the effect information, and we choose Wasserstein distance here because of this unique properties that the distance is symmetric here. So that's the reason why we actually resorted to Wasserstein distance here. And further, we can define the concept of integrated information. So let's say that this SIT is composed of distinct semantic content elements. So, okay, so our objective is to basically perform abstractions of these semantic content elements by filtering out irrelevant states. So we can how we define integrated information for a particular state SIT is that integrated information is the information conveyed by the states beyond that of what is conveyed by the individual semantic content elements. So that actually means that only if, okay, let's say the semantic content elements are all independent random variables, then there won't be any interactions between these different semantic content elements. So then the integrated information will be 0. So once there are some interactions between certain set of semantic content elements, so that means that there are some cause and effect relations between these semantic content elements. So yeah, so those set of states will form a semantic concept with non-zero integrated information. So that's how we can actually define a semantic concept or extract a semantic or identify a semantic concept from the data. So that's one step in terms of advancing the theory of semantic information that we actually proposed in this work. So further, I would also like to quickly discuss the methodology that we used for. So as I mentioned here, we have to, transmitter has to learn the causal graph, so which is achieved through causal discovery. And also this causal graph should be represented semantically. It should have a semantic representation, which is actually represented as ZT here. And then, yeah, so then the transmitter also has to compute a action control policy, which is pi export of action given the state, future state, current state, as well as the set of sensed variables. And then it also has to come up with this transition distribution, which is represented as a causal graph. So this, okay, given that we don't have a we do not have we do not have information of the true posterior distribution of this causal state transition, we actually resort to using a variational Bayesian optimization approach here, where we compute an approximate distribution by minimizing the KL divergence, which actually can be formulated as maximizing the evidence lower bound. So that's this G expression here. And that's how we actually formulated the causal graph computation problem. And also at the transmit side, there is also the problem of computing the semantic states. That is achieved as, so that is formulated as maximizing the integrated information conveyed by the causal state about the YT, which is the corresponding to the inference variable at the receiver side, subject to constraints on the bandwidth. So how much information this ZT conveys about ST should be less than or equal to some threshold. So that actually tells about the bandwidth constraint. So there are two different problems here. So we solve these two problems by formulating this causal graph as well as this causal graph as well as the semantic representation using generative AI based neural networks, wherein specifically for causal graph we used a graph neural network concept, and for semantic state representation we actually used variational autoencoder based framework to represent that. And we actually solved this two-level optimization problem by a nested optimization using gradient descent. So that's how we actually solved the parameters of the neural network. I won't go into the details of the problem solution. So instead, I would like to further state certain simulation results that we had. So first is what we showed through this generative AI based framework is that, or the world model based framework as I discussed here, is that we actually showed that compared to classical maximum likelihood based transition modeling, our proposed causal semantic communication system can better represent the network state for diverse SNR ranges compared to classical systems. And also we showed the generalizability by considering that, okay, so we started with some particular network or autonomous agent environment. Then after around, let's say 6K samples, we actually changed the environment dynamics. Then we actually saw that the classical systems will take, the traditional system, which are basically data driven AI based algorithms like transformer based encoder or decoder, that takes large amount of time to actually recover back to the normal state. But our causality based system is able to adapt quickly to this network dynamics. So that actually proves the dynamic adaptability aspect. Yeah, so that actually concludes my work on causal semantic communication for digital twin based systems. So further, I would like to quickly discuss some future perspectives. As I mentioned, currently I've been considering only a point-to-point semantic communication system. So my next goal is to actually consider a multi-user semantic communication system, wherein, okay, so these set of uses are, okay, this could be robots or humans, so they, or a combination of them. So they are actually engaged in solving a particular, uh, maybe a shared task or a or distant task it can be. So therein, the objective is to design a joint communication and control system. So herein, we can consider that each of these user has access to only a partial observation. So basically a case of partial observable Markov decision process. So that way we can actually formulate that. So using this partial observation and also using the communicated information from other users, each user should form a world model about the environment. Yeah, then the quality of the, using the world model that they construct, they come up with a shared semantic language or shared symbol system. Yeah, so that actually will depend upon the quality of the world model learned by each of the users. So here, a promising approach is to actually use the perception and action planning framework, design a perception and action planning framework through active inference concept. So in this direction, yeah, so I'm actually looking at formulating the semantic encoder or causal representation frameworks as follows. So let's say we have a semantic encoder. So that is defined as an approximate distribution, which is Q of UT, where U is the semantic symbol, and ZT K correspond to the causal states pursued at different uses, where K corresponds to user index. And then causal representation at each user, we can actually consider it as Q of ZTK given ZT minus 1, UT minus 1. And here, OTK corresponds to the partial observation at user K. YT minus 1K corresponds to the inference decision in the previous time slot for user K. So here observation, basically it's like composed of two aspects. One is like the partial observation and also like the inference decision that this particular edge user will make. Yeah, so basically the causal representation or the world model actually changes based on the inference decisions of each user. And yeah, semantic symbol prior is P of UT, and then the logical reasoning and observation model, we can actually formulate it like probability of YT plus 1 given ZT times probability of OT given YT ZT. So observation depends on inference decision as well as the causal state. And then the actual transition model will be as is shown here. Yeah, so here, yeah, so actually motivated by the formulations in this recent paper that appeared in Archive, we can actually formulate the collective free energy based, yeah, we can actually write the collective free energy for this particular particular multi-user semantic communication system. So yeah, so wherein I'm not going to the details of this mathematical expression, but we can write this free energy term as consisting of three different factors. So one is the reconstruction aspect. So how much the user can actually reconstruct the observations based on the causal world model. And then the second term is actually corresponding to the causal dynamics approximation, which means how much the each user can approximate the causal world model based on the observations, partial observation at its end. And the final factor will be corresponding to the a term that actually regularizes the entropy of semantic encoder, which actually means that, so this term would be actually corresponding to the to minimizing certain communication cost. So, or basically ensuring that we communicate minimal semantics from the data. Yeah, so we can actually formulate two phase, like an active inference. We can actually formulate the free energy expressions for the perception phase and also for the inference phase, which is corresponding to, where y corresponds to the inference variable. And so then the objective is basically using the free energy for the perception part. We can actually compute the minimalistic semantic encoder or the common semantic symbol system, as well as using the inference free energy framework. We can actually compute the best inference decision that each user should make using its own causal state perception as well as the communicated information. So that's the framework that I think can be applied for this multi-user semantic communication systems. So that will, with that I will conclude my talk. So as I mentioned, 5G could not meet all the promises. However, as we move towards next generation system, wherein so the communication networks are not just about building better wireless, better standard, better systems which high data rate or low latency and so on, but also incorporating aspects like sensing or trustworthiness, and also autonomous control of distant agents or cyber physical system. So we should transition to a telecom brain-based vision, which is consisting of modules like sensing, perception, world model, and action planning. And I discuss in detail few of our work on semantic communication, where we actually showed that using causality and neurosymbolic AI, we can actually build minimalistic, generalizable, and high fidelity semantic system. So they're saving a lot of the bandwidth. And then, the future research vision, my future research vision is centered around building sustainable, trustworthy, and socially responsible NG-AI native wireless systems using the telecom principles. So with that, I will conclude my talk. And if you have any questions, I am glad to answer those.
Thank you for the awesome presentation. Okay, I will prepare my questions and also welcome anyone in the chat to write. And just while I crop and prepare that, just could you share a little bit? How did you come to be setting up the lab? Like, just what was your trajectory from through school on through here? How did you get into this research area?
So I did my PhD in fifth generation wireless communications with focus on the physical layer aspects, like building, developing beamforming solutions or channel estimation schemes using conventional signal processing algorithms, like specifically even approximate Bayesian inference kind of techniques. So those are my main focus during my PhD. But when I transitioned to a postdoctoral position, I choose a different path. Like, I saw that the physical layer advancements is kind of, all the physical layer literature is kind of saturating out. So we need some new revolution in communication system as we move towards next generation systems that can be feasible by the incorporation of AI, but not just data-driven AI, but AI that can actually reason like human beings. So that is the motivation why I started to work with Professor Walid Saad on this particular topic. yeah, so that's how I actually entered into semantic communications, which is actually a revolutionary approach uh, that is aimed at build and improving the resource efficiency of future communication systems. So yeah, so that's how I ended up at this particular research.
Thank you.
Uh,
Well, I'm extremely appreciative to your colleagues and you for bringing this all together, and I'm excited to see where this all heads. Because it's aligned with many of my interests, and I also believe it's a critical infrastructure kind of civilizational technology layer. So, first, I tried to summarize in one sentence because there are so many pieces and so many formalisms that might be new. So, my one sentence summary was dynamics and constraints of semantic transfer in hybrid and synthetic network intelligence systems. And then to kind of expand on that a little bit, so I'll just make a remark about where I saw active inference coming into play and some of the important areas. So you starting with a dyadic model, templated dyadic communication models like teacher-apprentice or adversarial models, you are looking towards using active inference to allow real-time cooperation and turn-taking in multi-agent systems. And that would allow the embodiment, which is achieved in different engineering solutions in different ways. However, the top-down approach is what is the analytical formalism that gives a unity from a modeling perspective to all of these different engineering approaches. And those formalisms that you presented on allow the embodiment of agent or situation, class, instance, and context-specific cognitive mechanisms and dynamics, which broadly correspond to perception on the inbound and action selection and on the outbound with reasoning happening in between. And so what that is heading towards is a first principles approach that applies to semantic dynamics, which could be used within a single-threaded shared database state multi-agent system. So it could be a system with a very specific logistical order or known computational resource constraints, all the way on through nested arbitrary systems, and then importantly, embodied cyber-physical networks, where there can be the explicit introduction of physical and energy models, bandwidth and resource costs. And so that brings a complementary view from the engineering side on informational and cognitive constraints with important physical constraints of the ever-changing basis of networks. So just kind of wanted to echo back because there are so many important pieces in the talk and it was a lot of information and it's a part of our tech stack that just kind of works. Like the phone just has service and it's really abstracted. And then, of course, we know that the phones are coming out with different versions. And I'm not knowledgeable in these areas that much, but it's like service is different in different regions and things change and technology happens like that. So giving that kind of view into the tech stack is also, I think, really critical. So usually I do not give a sort of extended comment, but I was writing down so many notes. So do you have any thoughts or ideas on that?
Yeah, I think you have described, the summary of this talk, and quite well. That's a great summary. So one point just to conclude is that, like, so right now with 5G, we are able to get large download speeds or lower latency, streaming and so on. But when we actually move to next generation system, it's not just about the cellular communication. So the network should also, we should be able to build much more smarter environments, like smarter transportation systems or smarter industries, telehealth systems. So that actually requires the network to actually have a perception about the physical world. If the network has to control the operations of these distant autonomous agents. So the network should have a accurate perception about the physical world, unlike in classical system where we just treat the communication systems just like a passive system. So whatever message comes in, the objective is just to communicate that messages with high accuracy at the receiving end. So that's a transitional paradigm that we are looking at as we move towards 6G or 6G and beyond.
Yeah, another area I wanted to remark on, and part of that transformation is predictive processing and the role of prediction in compression. So the predictive processing frame differencing is used in standard syntax information driven compressive systems. Like frame differencing in the video, if all you have to do is transmit what changes between frames, it gives within a given local minima of minimal compression. And that was discovered in the computer science area, and then actually entered into this broader discussion about like visual and sensory systems. So that's using frame differencing to, for example, transmit a 4K video with less syntactic information flow. And then actually it goes even further with all of your work exploring the transfer in a latent or semantic space, which could be more like a primary lexical semantics or conceptual modularity, all the way up on through possibly complex pragmatics like action directives or complex information being shared at a higher semantic level. And then that's kind of again where active inference comes into play, is having a unified framework that on one hand can give an account for why frame differencing at a purely sensory kind of Shannon information level is a compressive strategy, and then use on a latent space in exactly analogous formalism, a cooperative mechanism to enable semantic compression. So like if we both have a friend ABC, but we both know them as A, then there's the question of the bits per second of the audio transfer, like how good is my microphone and how much data needs to be sent. But maybe a given bandwidth, you only need to say A, because B and C are semantically known. And so that just kind of shows like it's not just about the amount of data transmitted. Compressing it, all other things being equal, is good. Why send extra data through the wire? But now, and this is kind of where I want to hear your thoughts on this, we see a lot of work with natural language intermediaries. And that is used to transfer information broadly with this kind of natural language interface. But also we could imagine situations where semantic information transfer happens on networks. And I think this is exactly what you were getting at. So what kinds of information can be transferred? Like, does transmitting vector embeddings have markedly different semantic impact than, for example, dialogue between LLMs? Like the kinds of bandwidth that are currently being used in natural language mediated transmission, could strategies like multimodal or semantic compression give some kind of order of magnitude modifications in the bandwidth or the impact of communication amongst latent space?
So one way to look at it is like, okay, so let's say if you have like two LLM agents communicating, and let's say, okay, so they are using this natural language to communicate among them. So let's say, okay, so in semantic communication, so we are not, I mean, so we are not really concerned about how LLM agent 1 communicates in a in grammatically correct English sentence, with all the details included to LLM agent 2. Rather, we will be more interest here. We are actually, our frameworks actually lead to, okay, following this emergent language formulation. So as time progresses, what these LLM agents would learn is that, okay, let's say they're still communicating using English letters. So they end up learning a language, okay, communicating a sequence of words or letters that is sufficient enough for the other agent to understand it. I mean, it need not be, it can be considered like a machine language, which need not be perfect like an English language, but certain sequence of letters that is enough for LLM agent 2 to actually understand LLM agent 1, given the background knowledge that each agent has. LLM agent 1. So okay, so when two humans actually start communicating, okay, when two new yeah, so when I start communicating to another person whom I don't know before, so initially there is a lot of overhead, like we have to introduce ourselves, we have to share some background knowledge about ourselves. So then further, as they become friends, so then when they communicate, so they have a lot of implicit assumptions about the other person, how that person would be thinking, or how that person would be viewing the world around him. So the communication would actually be more more optimized considering also that background, right? So similar to that, so yeah, so if two LLM agents communicate among them, so using an emergent language framework, our objective is to build a machine language that is sufficient enough for LLM agent to pursue or understand what LLM agent 1 actually means. So that is so that kind of a machine language construction leads to a better usage of communication resources. So does that make sense to you?
Yes, like where that kind of takes me is when we're talking about emergent semantics and pragmatics, which could be between family members, it could be between strangers, humans, it could be online or in person, it could be two LLMs, it could be a person and LLM, like every kind of combo. Having this approach gives a way to scaffold the informational dynamics and kind of separate out the syntactic layer from the semantic layer, and then it naturally leads to these kinds of sustained duration semantic learning strategies. Like if every single message was coming from a different source, then there would be some sort of like no free lunch, but you could take the best semantics as possible to each fresh source, like if it was just a different every single time. But then to the extent that you can have a prior about a given type of interaction all the way on through the most specific prior, which is exact relational with a given other entity, then that allows semantic communication strategies like 1 means this dinner and 2 means that dinner. Well, then they only have to send 1 letter. And then when we get into these situations where it can be machine semantics, then that's kind of what tokens are. Like that's why words in a given language get truncated up into these essentially probabilistically determined semantic units. Like, oh, it's this verb and then ed to be the past tense. So it's like, or whatever the tokenization strategy happens to be. And then how do you use your tokens to have this no regret or minimal regret, best possible token conveyance linearity to finesse the translation of elements of a semantic space, which could be static or dynamic, into a linearized sequence of messages. And then the network perspective is really important because network properties can matter. Like if you have a network where 100% of packets are delivered, you're going to have certain kinds of strategic constraints in communication. Whereas if you have a network where a given percent are being at this, redirected, or this kind of etc. is happening. Like those physical constraints do matter for a communication strategy. And so having a sort of integrated analytic approach to modeling explicit syntax constraints, classical Shannon syntax, entropy-driven computer science and networking, on through abstract cognitive informational constraints, like we're just going to assume that it could be the maximally informative symbol. Like the letter distribution in natural language could be made more informative. So using some rebalanced even A through Z, there could be increased information transfer, but that would only be in certain situations, like a machine-machine situation might be able to do that kind of hacking into the actual symbols being set in plaintext. But that just, again, reflects on how there's both the particular network and symbol set constraints that are really, really well laid out from a Shannon syntax approach. And then there's this outer space, which we're still just beginning to explore, that is grounded in the primary symbol entropy and the observations. However, it can have multiple layers of cognitive and metacognitive dynamics, which are not so closely bound to the primary Shannon constraints, but still do have important constraints of their own. However, that's what semantic information is about, because semantics can be about semantics. I think that was one of the questions on one of the slides, which is like cognition on cognition or metacognition.
Right. Yeah, so it's like above this communication constraints that we have, we are effectively forming a semantic layer between the transmitter and receiver, which is actually constrained by all this cognitivity, and then the understanding aspects, right? So, that's very insightful discussion.
Thank you. Yeah, well, just in sort of closing, what are your next steps, or what are like the timeline with the lab, or how would people learn more or get involved?
I'll be starting my new position from August 2025, and I'm looking to recruit 1 to 2 PhD students. And also continue this work with the students on this particular topic. And I do have a lab website which is still kind of under construction, but I can share this. I will share all my updates through this website.
Awesome.
Happy to discuss further, or even give a talk later when I have more results.
Cool. Well, again, very appreciative of the work and the concise presentation. Wish you the best. Till next time.
Thank you very much. Thank you for the invitation.